Section 2.3, Linear Functions and Slope. We use the variable m to refer to the slope of a line. When the line rises from left to right, we say the slope is positive, and when it's going down from left to right, we say the slope is negative. If it's going horizontal, then the slope is 0. And if you can't go from left to right at all because the line is vertical, then there's no slope. M is undefined. The slope can be found using a formula. The idea is that it's the change in y, the rise, over the change in x, the run. To find the vertical change, we subtract the two y values, and to find the horizontal change, we'll subtract the two x values. Note that we can't divide by 0, so the difference of the two x values cannot be 0, which means your 2 points cannot have the same x value. Let's take a look at an example. Find the slope of the line passing through these 2 points. We'll use our slope formula. It doesn't matter which point you consider point 1 and point 2, but usually we take them in the order that they're there. So our second point has a y value of 5, so we'll write that on top. It has an x value of -1, so we'll write that below. Then note that the formula has subtractions, so we put those into our equation. And then we look at our other point. Its y value is -2, so we write that up top. And its x value is 4, so we write that on the bottom. 5 minus a -2 is the same as 5 plus 2, so we put 7 on top, and -1 minus 4 is a -5 on the bottom. We don't typically leave our slope with negatives on the bottom, so we will write that out in front. We could have put it up top and written it as -7/5, but that's our slope. Now we're going to look at some important forms of lines. The first one is called point slope form, and this is an important one when we're trying to write an equation because we'll often know the slope and a point. And so when we do, we will put it into this form. Let's take a look at an example. Write the equation in point slope form for the line with slope 6 that passes through the point 2, -5. Then solve the equation for y. There's our point slope form. We start by noting that the x and the y are variables and that the m is our slope, so we can write that in, slope of 6. And the point that they give us is 2, -5, so the y coordinate is -5. So we write that in for y sub 1, and we write in 2 for x sub 1. The only simplification that we need to do is to note that a -5 is the same as y plus 5. And that is the final result for point slope form. The question then goes on to ask us to solve the equation for y. To do that, we will first distribute the 6. 6 times x is 6x. 6 times -2 is -12. Then we will subtract 5 from both sides. When we subtract 5 on the left, it leaves us with just the y. And when we subtract 5 from -12, that gives us a -17. So solved for y, we get y equals 6x minus 17. Note that when you're working on exercises in this section, that you'll want to look very carefully at what form they're asking you to write your equation in. In this particular exercise, they asked for point slope form, and then they asked us to solve it for y. Solving for y is actually the next important form that we're going to talk about. This form is called slope intercept form. The reason this form has this name is that once it's solved for y, the coefficient of x is our slope, and the constant is our y-intercept. So this is slope intercept form. One use of slope intercept form is when we go to graph. There's a nice method we can use. The first step will be to plot the point that contains the y-intercept. Since the y-intercept is the constant that is in the equation, we can go to the y-axis and go, if it's positive, we'll go up that far. If it's negative, we'll go down that far. We can plot that point. Then we can get a second point by using the slope. Remember, the slope is the coefficient of x when the equation is solved for y. And when that slope is written as a fraction, The top number is the rise, so that'll tell us how far up or down we should move from our first point. And the denominator of that fraction is the run, which will tell us how far left or right to move. Once we've plotted those 2 points, we can take a ruler and draw a line through those 2 points, and we draw arrowheads on the ends to show that it goes infinitely in both directions. Let's take a look at an example. This line is in slope-intercept form. Note that instead of y equals mx plus b form, it says f of x. Hopefully you recall function notation. This f of x is a way of writing y in what we call function notation. If you are less familiar, please note that this does not mean that we're multiplying something, variable f times a variable x. This is not multiplication. You'll need to review function notation if this is looking strange to you. But the rest is the same, so let's continue. The first step will be to plot the point containing the y-intercept. Since the y-intercept is 1, on the y-axis, we put a point that is plus 1, that is up 1 on the y-axis. We then need a second point, so from that point, we'll use the slope. The top number is the rise, so from the point we just plotted, we're going to go up 3, and then from there, we're going to use the run of 5, which means we're going to go to the right 5. When we go there, we can plot that point, which is the point 5, 4. And then finally, we take those 2 points in a ruler and we draw a line through it with the arrowheads on each end. The next important form of a line that you'll need to know is when it's a horizontal line. Horizontal lines are given by the equation y equals b, where b is a constant, and that constant is the height of that line. Remember that the slope of a horizontal line is 0. Let's look at an example where they're asking us to graph y equals 3. Y equals 3 is a line where every y value of every point will be 3. It wouldn't matter what x's you pick, so we can just pick some arbitrarily. If I come back here at -2, when x is -2, y is at a height of 3. If I come where x is 0, when x is 0, y is at 3. And when I'm over at 2, y is at a height of 3. So y is always at a height of 3, and so we can then draw our line at that height. It's a horizontal line that goes through this value of 3. Next, we'll look at vertical lines. Vertical lines are of the form x equals a constant, and that constant will tell us the x-intercept. It'll tell us where it's crossing the x-axis. Recall that the slope of a vertical line is undefined. So let's look at an example. We're going to graph x equals -2. So we go to our graph paper, and we can come back 2 units, and we can draw our vertical line through where x is -2. Notice that any point on this line has an x value of -2. So notice we didn't need a chart to do this one. We can just use the concept of a vertical line through the point where x is -2. The last form we're going to look at is general form. General form is when you have your x term, your y term, and your constant all on the same side of the equation. There's a few other requirements. A, B, and C are any real numbers, but A and B can't both be 0. Let's look at an example. Here's a line that's in general form. They want us to find the slope and the y-intercept. So when that's the case, we typically will solve for y. We'll write the equation in slope-intercept form by solving for y. So to do that, the first step is we want to get y by itself, so we want to get rid of the 3x and get rid of the 12. I use what's called transposing, where you can take this term and just move it to the other side by changing its sign. And I did that with the -12 as well. I moved it to this side and made it a +12. But notice that this comes from basic algebra. If I have a 3x here, if I subtract 3x, it disappears on the left. And if I have 0 and I subtract 3x, I get -3x on the right. Same thing with the 12. If I add 12 to the -12, then it disappears on the left. If I add 12 to 0, I get the +12. So the quickest way is if you have terms that you would prefer to be on the other side, you can just move them and change their sign. At this point, I need y by itself. Since they're multiplying it by 6, the next step in simplifying this is to divide each term by 6, because then the 6's cancel, giving me just y on the left. And then I simplify these fractions and I get -1/2 and 2. So remember, the goal was to solve for y. By doing that, we now have this in slope-intercept form. So that means that the coefficient of x is the slope. So the slope is -1/2, and the b term is the y-intercept. So that means that it's a y-intercept of 2. Next, we can use intercepts to graph an equation that's in general form. Remember, when you're asked to graph, there's multiple possible methods to use, but one nice one when it's in general form is to find intercepts. To find the x-intercept, we let y equal 0, and then we solve for x. To find the y-intercept, we let x equal 0 and solve for y. I'll show you an example of this in a moment. The third step, as usual, is to draw the line that goes through those 2 points. As long as A, B, and C, as long as none of them are 0, this method works really well to graph a line in general form. So let's take a look at this example. We want to graph using intercepts. So first we want to find the x-intercept. To find the x-intercept, we let y equal 0. So that means we'll go and replace y with 0. So we just get 3x minus 6 equals 0. We can now transpose the 6. We can take it to the other side and make it a positive 6. And since we want x by itself, we'll divide both sides by 3, which gives us x equals 2. So that tells us that the x-intercept is 2, so that's going to be one of the points that we plot. To plot that point, it's an x-intercept of 2, so we put it on the x-axis at positive 2. Next, we want to find another point, which is the y-intercept, by letting x equal 0. So out goes x, in goes 0. That will zero out this term. So we just have -2y minus 6 equals 0. Again, we'll transpose that 6. Transposing says take it to the other side and change its sign. And then finally, we want y by itself, so we have to divide both sides by -2. When we divide this side by -2, it cancels it out. We get just y. When we divide 6 by -2, we end up with -3. And so that is our y-intercept, and that gives us a second point to plot. So we finish this off by plotting both points. The x-intercept was 2, the y-intercept was -3, and we can draw our line through those 2 points. Let's look at a summary of the various equations of lines. The first one we looked at was point-slope form, and this form is especially useful when you have information about a line, but you don't have an equation, so you want to write the equation. The next one was slope-intercept form, y equals mx plus b, and this form is useful because it tells us the slope and the y-intercept. In addition to having this as y equals mx plus b, they sometimes write it as a function f of x equals mx plus b, but that's the same form. The next one we looked at was the horizontal line, y equals b. That one is for horizontal lines, and we can also write that as the function of f of x equals b. Then there were vertical lines, that's x equals a. Remember, vertical lines, they cannot be written in function notation because vertical lines are never a function. And then finally, we looked at general form. Now let's look at an application problem. This one says use these points to obtain a linear function that models average global temperature, f of x, for an atmospheric carbon dioxide concentration of x parts per million. Round m to 3 decimal places and b to 1 decimal place. Well, to write the equation of a line, we use point-slope form. That was the form that we said is the most useful for getting things started. The problem is we don't have the slope. Because they gave us 2 points, we can find the slope. So we'll take those 2 points and run them through the slope formula. It asks us to round m to 3 places, so we don't leave it as a fraction. We just do top divided by the bottom on our calculator and then round to 3 places. Note that it also says that we want to round b to 1 decimal place. We don't yet have b, but that's going to take place on the next slide, so I just want you to remember when we get there that we'll round that to 1 place. How will we finish this off? Recall that the point-slope form, you need the slope and a point. Well, we just found the slope. It's 0.016, and we have 2 points, and when you have 2 points, you can just take your pick. So I'll pick this one. So now we have point slope form, and let's take that to the next slide and finish this question off. It said find the equation. Here's our point slope form. So we take our slope and plug it in. We take the point that we selected. Now, you might wonder why you get to choose which point. It turns out that once we do all the work, it's going to give us the exact same answer. So you could test that out if you wanted to try it with the other point. We want to write this as a function, so we don't leave this in point slope form. It said find the function, so therefore we'll have to solve this for y. So we'll distribute this slope to the x, and then we'll multiply this times the 354. We get 5.664. Then we add 57.64. We get the 51.976, and this is our b. And recall they wanted us to round that to 1 decimal place, so we get 52.0. They asked us to write it as a function f of x, so instead of y notation, we rewrite it with f of x notation. That is the function that will model average global temperature for a particular atmospheric carbon dioxide concentration of x parts per million. That's example 8a. Let's take a look at example 8b. It's going to ask us to use this formula in the following way. In 2023, the atmospheric carbon dioxide concentration level was 419 parts per million, and the average global temperature at that time was 59 degrees Fahrenheit. Did the function we found overestimate or underestimate the actual temperature? So we'll take our function and we'll substitute in the parts per million, which is our x of 419. So f of 419 will be obtained by running this through our calculator, and that gives us approximately 58.7. Now 58.7 is what the formula gives us. The actual temperature at that time was 59 degrees, so our function underestimated by just a little bit. The function underestimated the actual value of 59 degrees by 0.3 degrees.